Thank you very much. Actually, the title itself is so complex. There are so many different pieces, and that's one of the interesting parts of this work, that bringing together a lot of different technologies, from Intel FPGA hardware to Apache Spark, and putting it in the context of a very useful application, which is analyzing risk for financial applications. This talk is mostly about analyzing risk on financial applications. However, that's not a limiting factor. Basically, risk analysis is applicable in many other areas as well, pretty much the same framework. So the first three slides are three slides that I have taken snapshots of a YouTube of a talk by a gentleman from Goldman Sachs at Amazon's reInvent. And if you look at this, you will realize that some of the largest, most advanced technical companies in the world are not from 21st century, they are from mid-19th century, and those are banks. A bank is a modern bank right now is a technological powerhouse. They employ thousands of software engineers, they write billions of lines of code, and they manage hundreds of thousands of servers. And one of the three main applications in a bank is analyzing risk. So analyzing risk, it's a very fundamental part of what they do. And in order to do that, they have to process a lot of data. And the more data and more diverse data they process, they can come up with a better model, and they can process and they can do a better job in analyzing risk. They can make more profit. They can reduce their losses. And to do that, there are a few things that are important for them. One is that time. If you look at the metrics over the history of computing, the metrics that was very important at the beginning was like capacity of the data that you could store, or the speed that you could do processing. Then at the age of web, it became throughput. You know, how many concurrent customers your website can accommodate at the same time. And now at the age of self-driving cars and things like Uber, and the most important metrics is becoming latency. So latency is becoming more and more a differentiator, and it's becoming more important to be able to process the data as soon as possible. So in order to reduce that latency, you have to be able to do a lot of computation, and very sophisticated computation at a very short amount of time. At the same time, you have to do it on super large data sets. So you have a lot of data, you have a lot of diverse data. The size of this data is increasing rapidly. You have a lot of calculation, and now you have a lot of diverse and sophisticated calculation in order to do the risk analysis. And that actually makes cloud to be a perfect platform, because you have a lot more flexibility in the type of data that you're accessing, the type of computation, and the size of it. And that's why we see that a lot of more fancier, more sophisticated type of hardware are becoming more and more available on the cloud. You have new type of, like you have SSDs, now you have GPUs, FPGAs are available on the cloud. The problem with these things is that a lot of these are not very easily usable. Like a regular programmer or someone, application developer, may not be able to code for FPGA or easily optimize its code for GPU or for SSD or other types of storage media that it's new. And what we did some work with Intel, bringing frameworks that allows these users to be able to use the combination of all these technologies. You know, FPGAs, very fast, persistent memory technologies, distributed computation frameworks like Spark, and use it for an application like financial risk analysis. And we took this example, something called backtesting that, you know, Mutema is going to talk about it more, but basically using historical data to train a new model. And the interesting thing about it is that it has two interesting components. One is that you have to process a lot of data because, you know, if you look at the transactions in the stock market, there are like billions of transactions. So if you look at the history of the transactions, you see like tens of terabytes of data. And now, at the same time, the regular analysis of this data is basically you look at this stock market data, see like when, for example, the two different moving averages cross, and based on that, you come up with a framework so that if at this point I should sell my stock or buy this stock, and then calculate, see how much profit you would make if you had done that, and make a model based on that. That's obviously a very simplistic. The real models are much more complicated. Now doing that with the options, with things that have a higher degree of risk element, is much more sophisticated because now you have a lot more variables. You have things like the expiration date, you have the volatility parameters, you have different strike prices for the same option. So if you have a table which is like 1 terabyte, when you take into account all of these elements, that 1 terabyte may become 20 terabytes, 100 terabytes, 400 terabytes, because you multiply that, you know, by, you know, you basically take the same number and span it across multiple dimensions. Now, so doing that with options and other instruments are much more sophisticated than doing it with the regular stock. So there is a consortium of financial institutions called STACK that does measurements of this type of calculations, and their usual metric is the cost for doing 1 million transactions in 1 hour, 1 million simulations. So you run 1 million simulations in 1 hour. And they do it for regular stock. Now, if you want to do that for options, as I said, your tables are much larger. So you can use FPGA, of course, to reduce the time that it takes to do the computation, but how much data can you fit in that FPGA? So you have to find a platform that you can push that data into FPGA, do the calculation, and keep the result somewhere to do your analysis. And that's something that we call persistent data frames. Actually, there's a typo here. I should have said persistent data frames, not persistent RDDs. And these data frames reside on flash. They get so when you do the calculation from Apache Spark comes to the connector that we have built, and it's compiled on the fly, and calculates those tables part of the calculation has to call the financial libraries that reside on the FPGA, and that's done automatically. And then the results are written in a format which is exactly like a regular data frame. So Apache Spark sees it as a data frame, but it's actually persisted on SSD or in this case, Intel Optane products. So this way, you don't need to recompute. You don't need to go to HDFS or S3 or wherever your data is and bring it, do the calculation, and then when it finishes, go to HDFS again and bring the data again. Also, if you have multiple simulations or multiple groups that are running different simulations on the same data sets, you can do all of them concurrently on the same live data sets. Basically, you're sharing the same data frame across multiple applications. And so this will help a lot, especially when the data size is like in terabytes or tens of terabytes. So the overall architecture, as I mentioned, is like this. So at the top, there is the risk management platform, the applications that banks write. The interesting thing is that they don't really need to change their application. So if they have written it in Scala or Java or Python, it works fine. And so they use a Spark, and then when the query comes, it's compiled on the fly. Part of it is executed on the FPGA, and then is written to persistent data frames. And then the analytic part runs again on Spark and calculates, does the analytics. If you look at the results, this is, we have different results that actually some of this has been already showcased in some of the, financial gatherings. So the number of symbols, like we start from 4 to 80. So that means the number of, the history of like 4 different stock tickers, like IBM and Google and Microsoft and Apple, something like that. And then based on that, you have a lot of transactions that has happened. You calculate the number of options, which is, as I mentioned, spanning across different dimensions, like based on, in these cases, we have limited the number of those dimensions. It could expand to much larger. And the reason that we limited it is that, the size of the Optane drives that we had wouldn't allow us to process like a 40 terabyte data set, so we could do only a few terabytes. So we have these super large tables, and then when we run it, we can analyze about 53 million options per second versus like 17 million if you just use Spark without this layer. So then, Mutema from Intel is going to talk to you about the details of how the FinLib works and conclude the session.
So it probably wouldn't come as a surprise to those who know me or know the area I work in within Intel that I believe that FPGAs are a great hardware accelerator. So like Reza said, my name is Mutema Pittman. I work within the Programmable Solutions Group within Intel, formerly Altera. One thing that we know, in order to succeed within the data center, you not only need to have really a compelling value proposition, you also need to be easy to adopt. And frankly, that's not something that one traditionally thinks of when they think of FPGAs. So that's what we're trying to change here. And it all starts with our hardware platform. We call it the Intel Programmable Acceleration Card. So it's not a dev kit, it's not a demo card. This is a fully production card that goes through a lot of steps to get there in order to make it easy to adopt. It's available in the highest volume servers with all of the large OEMs. But we don't stop there. We build on a software stack onto this hardware platform. And really the beauty of that software stack is it abstracts away a lot of the traditionally difficult things about FPGAs. You don't need to worry about the connection to the PCIe. You don't need to worry about the connection to memory. You don't need to worry about the connection to the networking interface. All that is taken care of. So whoever is developing their application, they can focus on what they're good at, so that their actual workload, and everything else is just plug and play. On top of that, we build out these primitives. So these primitives are really what abstracts away from the FPGA. They allow software programmers really to come in, and this entire platform really is meant to be a way to bring together FPGA programmers and software programmers so that they can work together and really achieve things that maybe we didn't even think of. Those primitives, they're wrapped into pre-compiled kernels, and that exists within a library infrastructure that can be accessed through OpenCL, through an API, through any software developer. And as Reza certainly alluded to, that framework, whether it be Spark or something else, allows for access to those libraries, access to that hardware, without actually knowing that the FPGA is a part of the equation. What we're really trying to do is democratize the use of FPGAs and make it easy for anyone to use. Obviously, there's a much larger software base out there than FPGA base, and we want to really engage that base to create solutions that are far beyond what we imagine today. So this is a snapshot of our financial libraries. We had our marketing team work around the clock to come up with a very creative name. FinLib is what we arrived at. Reza talked a little bit about FinLib in terms of how he incorporated that. And really it's a subset of FinLib in which he worked with, really two pieces. One is the Black-Scholes model, which is used for European options. The other is Cox-Ross-Rubinstein, used for American options. And both are used in the context of backtesting. So basically a trader has some type of strategy algorithm that they want to test. They test that against historical backdata. And as Reza said, that can be a very large set of data. And you can imagine the quicker that they can do that, it certainly holds advantages. If you can do it very quickly, you can make more modifications to your strategy. If you can do it quickly, you can perhaps test more strategies in parallel. And obviously with these big financial institutions, that time equates directly to money. We'll be moving forward in FinLib Phase 2, but one thing I do want to stress here, and what I think is probably the most cool thing about this, is how people are able to use these libraries. So Levyx, they're not an FPGA company, they're a software company, they're a storage company. And the beauty of what they were able to do really is feed that information into the FPGA, but they're not FPGA programmers. And yet they were able to see the benefits of that acceleration and create a demo around that in about 4 weeks. So that is really compelling. You're able to really shorten the amount of time that you can get these solutions up and running. And that's where we want to be. That's where we have to be in order to make FPGAs accessible to the rest of the world. In FinLib 2.0, we'll be expanding the libraries. We'll be moving into some more high-level functions like PDE solvers for 2D parabolic equations. We'll be building out Monte Carlo simulators, which obviously are not just applicable to finance. They're applicable to things like insurance, fraud detection, oil and gas, so many different areas. And that's the goal here, to really build up a type of framework, a structure similar, not too dissimilar to MKL, where a lot of software programmers are familiar with the context of what they would be building with. In FinLib 3.0, we build out more risk calculation models, whether it be from operational to shortfall. So in conclusion, I do want to stress here that the work that Levyx has done in conjunction with our platform, our libraries, really allowed a vast improvement in terms of performance. And a lot of that has to do with the way they were able to feed the data into the FPGA, and the FPGA acting as a natural accelerator. There was no real custom code here. It was just the software code built on top of libraries which are standard. And really, the ability of Levyx to use, whether it be NVMe or other types of memory, to scale up when needed and to right-size that memory, and bypassing the I/O. So you don't have to run into those traditional bottlenecks. You can write into the FPGA and really reduce the amount of time, and that's really where a lot of the bottlenecks come into play. Reduce those bottlenecks on the transactions back and forth. Okay, thank you very much.